What if a single day on a planet in our solar system lasted less than 10 hours, while on another, a single day is dragged on for more than 5,000 hours? It sounds like science fiction, right? But it's not. On Jupiter, a day is over before you can truly grasp it. But on Venus, a sunrise unfolds so slowly, you would never see it move. Both planets orbit around the same star, same solar system, but with completely different realities. So why does one planet spin with frantic speed, while its neighbor barely turns at all? To answer that, we have to go back 4.6 billion years, to a time when the solar system was not calm and orderly, but violent. Worlds were colliding and gravity was tearing out young planets, leaving a scar for every impact. A planet's spin is not random. It is a fossil record, a story locked into motion. From Earth's familiar rhythm to the dizzying extremes in the outer darkness, every rotation holds a clue. Today, we are decoding those clues to understand how planets in our solar system have so vastly varying rotation speeds. Hello everyone, welcome to another video from Deep Space Explained. Thank you for tuning in. If you are a subscribed viewer, thank you for all the support. If you are new to the channel, consider a like if you really like the video. Please share your feedback in the comments, and if you wish to, do let me have the pleasure of knowing which part of the world my viewer is tuning in today in comments below. Let's begin with something that feels stable and we are well informed about: planet Earth. Our lives are built around a 24-hour cycle. It governs sleep, biology, productivity, even culture itself. We assume it's fixed, permanent. But Earth is spinning at 1,574 kilometers per hour at the equator. That's faster than the speed of sound. You just don't feel it, because everything around you is moving at the same speed. But where did that spin come from? From birth. When the solar system formed, it began as a vast cloud of gas and dust. Gravity pulled that cloud inward. As it collapsed, it began spinning faster based on a principle known as conservation of angular momentum. Like a figure skater pulling in her arms, the tighter the collapse, the faster the spin. Earth was born from that rotating disk, and it has been spinning ever since. But here's something we rarely think about. Earth is slowing down. The moon's gravity pulls on our oceans. Those tides create friction against the ocean floor, and friction steals energy. It's like a brake pad gently pressed against a spinning wheel. For billions of years, 4 billion years ago, a day on Earth may have lasted only 19 hours. And it continues to lengthen. Even today, melting glaciers are redistributing mass across the planet, subtly altering rotation in measurable ways. Our 24-hour day feels eternal, but it isn't. Now let's step outwards towards our first neighbor, Mars. If any planet feels remotely familiar in its rhythm, it's this one. A Martian day lasts for roughly 24 hours and 37 minutes. Close enough that mission engineers operating Mars rovers actually adjust their sleep schedules to match Mars time. But why is Mars so similar? Because it formed in a relatively stable region of the early solar system. It inherited a certain amount of spin from the protoplanetary disk and has largely kept it. Its equatorial speed is about 866 kilometers per hour, roughly half of Earth's. Smaller planet, less mass, less angular momentum. Mars is what we might call orderly and predictable, but the inner solar system is not entirely predictable. For that, we will now move closer to the Sun. Mercury, a small, scorched planet. On Mercury, the idea of a day begins to collapse. Mercury rotates once every 58.5 Earth days. At the equator, it spins at just 10.8 kilometers per hour, slower than highway traffic on Earth. But why so slow? And the answer is simple enough. Mercury is locked. It exists in what is called a 3-to-2 spin-orbit resonance. For every 2 trips around the Sun, Mercury rotates exactly 3 times. This happens because the Sun's immense gravity pulls on slight asymmetries in Mercury's shape, tiny bulges that create torque. Over time, those gravitational tugs synchronize Mercury's rotation into a stable rhythm. It is not freely spinning. It is gravitationally constrained. Mercury can be tagged as our first major escalation in this regards. Rotation is no longer just about formation. Now gravity itself is shaping destiny. But even Mercury's strange rhythm is mild compared to what lies beyond the asteroid belt. As soon as we cross the asteroid belt in our cosmic journey, everything changes. The planets become massive, and their rotation becomes extreme. Let's take Saturn's example. A colossal gas giant wrapped in rings, yet it spins once every 10.5 hours. At its equator, Saturn is moving at 36,840 kilometers per hour. But why so fast? It's because when Saturn formed, it gathered enormous amounts of gas from the early solar nebula. And with that mass came angular momentum. The more material it pulled in, the more spin it conserved. And because Saturn is a gas giant, there is no solid surface to generate friction strong enough to slow it significantly. Its rotation is so rapid that Saturn is visibly flattened. Its equator bulges outward. It is not a perfect sphere. It is physically reshaped by its own velocity. But Saturn is not the fastest. It's not even close. Now let's talk about Neptune. It is cold, distant, violent in its own way. Neptune completes a rotation in about 16 hours with equatorial speed reaching up to nearly 9,719 kilometers per hour. Neptune slower than Saturn, but still far beyond any rocky world. Neptune formed in the far outer solar system, where less material was available. Less mass meant less angular momentum to inherit. Still powerful, still fast. But its neighbor Uranus certainly is more strange in comparison. On paper, Uranus seems ordinary. A day lasts about 17 hours, quite comparable to Neptune. But Uranus hides a secret. Its axis is tilted by 98 degrees, which means it does not spin like a top, it rolls. While other planets rotate upright, Uranus spins on its side. This means its rotation is retrograde, effectively backward compared to most planets. What could cause such a thing? Imagine a cosmic game of billiards. A glancing blow from a massive object, possibly Earth-sized, could have knocked Uranus completely sideways 4 billion years ago. Not powerful enough to destroy it, but enough to permanently reorient its axis. Uranus is a frozen relic of that ancient collision. Its rotation is not just motion, it is evidence of the solar system's violent past. Now we reach the true extremes. Let's start with the planet, which is extreme in many aspects. Jupiter, the largest planet in the solar system. It has more massive than all other planets combined. And to top it off, the fastest spinner of them all. A day on Jupiter lasts just under 10 hours. Its equator moves at 45,583 kilometers per hour. It spins so fast that early in its history, it may have approached breakup velocity, the point where centrifugal force could overcome gravity and tear the planet apart. So why didn't it? The leading theory suggests its powerful magnetic field interacted with the surrounding gas disk during formation, acting as a braking mechanism, siphoning just enough rotational energy to prevent self-destruction. Jupiter exists at the edge of physical possibility, and its speed drives everything we see. The banded cloud structure, the violent jet streams, the Great Red Spot, a storm larger than Earth that has raged for centuries. Its immense rotation also generates a magnetic field nearly 20,000 times stronger than Earth's. Jupiter is not simply spinning, it is a planetary engine, a dynamo powered by velocity. Now, we go from the most extreme to the most bizarre planet in terms of rotation, Venus. Venus is Earth's so-called twin, yet utterly alien. A single rotation on Venus takes 243 Earth days, but it orbits the Sun in only 225 days. Yes, you heard it right, and it means that its day is longer than its year. And to top it off, Venus spins backward. On Venus, the Sun rises in the west and sets in the east. But why? This remains one of the greatest unsolved mysteries in planetary science. One theory proposes a massive collision early in its history, powerful enough to cancel its original forward rotation and reverse it. This is the same theory that also tries to explain why Venus does not have a natural moon. We have discussed about it in details in a previous video. You can check that out if it intrigues you. Another theory suggests something slower and more subtle that resulted in this retrograde motion. Venus has an atmosphere over 90 times thicker than Earth's. That atmosphere generates immense thermal tides, vast movements of superheated gas. Over billions of years, the friction from those atmospheric tides may have acted like a planetary brake, slowing it, stopping it, perhaps even reversing it. It may not have been one catastrophic moment, but a billion-year tug-of-war between gravity and atmosphere, between inertia and resistance. Venus may represent the balance point of that struggle, a planet reshaped not by impact alone, but by its own atmosphere. Across our solar system, no two rotations are the same. Earth's has a familiar rhythm. Mars's has a near-twin cycle compared to Earth. Near-twin, not exactly the same. Mercury's is gravitationally locked. Uranus's sideways scar. Jupiter's controlled fury. Venus's backward rotation. Each one is a fossil record, a signature of formation, of collision, of survival. Rotation shapes weather systems, magnetic fields, climate. It even to some extent controls the potential for life. Our solar system is not static, it is dynamic, it is violent, and more importantly, it is still evolving. This brings us to the end of our video. Our solar system is filled with extremes. Which rotation fascinates you the most? Jupiter's impossible speed, or Venus's eerie backward rotation resulting in the Sun rising from the opposite direction? Tell me in the comments below, and until then, keep looking up at the stars.